Hello all. In my previous lecture, I discussed temperature effect on mobility in a semiconductor. Next, temperature effect on Fermi level in a semiconductor. Next, the temperature effect on conductivity in a semiconductor. And next, temperature effect on carrier concentration in a semiconductor. Now, in this class, I will start with drift and diffusion currents. So first I start with drift current. Right. See, what is a drift current actually? Drift current means the current can flows due to applied external electric field or potential difference. Due to this potential difference actually, electrons are moving from low potential to high potential, and the holes are moving from high potential to low potential, and it can produce a net current from high potential to low potential. That current is called as drift current. Right? That means the drift current depends on what actually? The drift current depends on applied electric field. Right. See here, in case of semiconductor, the current is due to two types of charge carriers, right? So first for free electrons actually, what will be the drift current? So for free electrons, the drift current is nothing but J naught drift equal to N into E into mu N into E. Right? Similarly for holes, and Jp of drift is equal to P into E into mu P into E. Right. Now from these two equations, what is the conclusion actually? The drift current will depends on what actually? It will depends on external electric field, and also it will depends on what actually? Carrier concentration. Right. This is about drift current. Right. Right down. The heading first one, drift current. Write on the notes. The current flows due to applied external electric field or potential difference. Right. Next point, due to the potential difference, electrons are moving from low potential to high potential, and holes are moving from high potential to low potential. And produce a net current from high potential to low potential. This current is called as drift current. Right. Now copy this one. The drift current is directly proportional to applied electric field, and copy the equations. Right. And next heading, diffusion current. See, this current can flows. The current can flows due to concentration gradient or concentration change. Right? Concentration difference or concentration change means, for example, if you consider a n-type sample actually, right, at x equal to 0, actually the concentration is maximum, right? And X equal to L, the concentration is minimum. I think there is a concentration difference or concentration gradient. Due to this concentration difference or concentration gradient, actually what happened? The charge carriers are moving from high concentration to low concentration. The charge carriers are moving from high concentration to low concentration, and this current is called as what actually? Diffusion current. That means the diffusion current depends on what actually? The diffusion current. The diffusion current depends on concentration gradient. Concentration gradient. Gradient means change. Right. In case of free electrons, what will be the diffusion current actually? That is Jn diffusion is equal to E into dn by dx. This dn by dx is nothing but concentration gradient. Here the concentration changes with respect to the distance. Similarly for holes actually, that is Jp diffusion is equal to minus E into dp into dp by dx, right? This is the diffusion current due to holes. Actually here the negative sign indicates what actually? This negative sign indicates, okay, indicates here the direction of the hole is moving oppositely to the bounded electron. That's why we are indicating with a negative sign. Okay, this is about diffusion current, right? Copy, write down first, write down the notes. The current flows due to concentration gradient or concentration change. Next point, due to concentration gradient, charge carriers are moving from high concentration to low concentration and produce a diffusion current. Right? Copy this one. Right. Write down where dn comma dpr diffusion constants or diffusivities. Right. I think I told dn by dx is nothing but concentration gradient and E is nothing but charge of electron, that you know, right? That means what is the conclusion actually? You know, in case of semiconductor, for example, if it is an n-type, okay, and what is the total current offered by a semiconductor actually? You know, the total current offered by a semiconductor is nothing but drift current plus diffusion current. That may be a n-type or p-type actually. Okay, and what is the conclusion, you know? And here in case of metal array conductor, only the drift current will flows, but whereas in semiconductor, okay, the both current will flows, that is drift current as well as diffusion current. And here my question is, why diffusion current cannot exist in conductors or metals? Because metals or conductors are uniformly doped. Uniformly doped means what about concentration gradient actually? Zero. Concentration gradient is zero. That's why diffusion current cannot exist in metals. It exists only in semiconductors. But the drift current can exist in both metal and semiconductor. But the diffusion current can exist only in semiconductor because metals are uniformly doped. So there is no chance of diffusion current. Okay, you know, and one more important point actually, in case of semiconductor also, the diffusion current can flows, diffusion current can flows in two cases only. One is if the semiconductor is non-uniformly doped. Semiconductor is non-uniformly doped means the sample is like this, n plus n. See here the concentration is n plus, here the concentration is n. I think there is a concentration difference, right? So in this case, the diffusion current can flows. And one more case, is, okay, the charge carriers are injected into a semiconductor, from one side by using carrier injection method. So in this case also, diffusion current can flows. What I am saying, in semiconductor also, the diffusion current can flows because of the two cases, right? One is if the semiconductor is non-uniformly doped, and another one is, okay, the charge carriers are injected into a semiconductor from one side. From one side means either this side or this side. See, so what happens if the charge carriers are injected from one side? Actually, the concentration here the maximum, and with respect to this one, the concentration is minimum. So there is a concentration difference. So which current will flows? Diffusion current will flows, right? Right on. Right on. Right on. In a semiconductor, the total current offered by, right on, J total equal to J drift plus J diffusion. J drift plus J diffusion. Right. Next observation. Next heading, observation. Drift current can adjust. Drift current can adjust both conductor and semiconductor. Drift current can adjust both conductor and semiconductor, but diffusion current can adjust. Only in semiconductor. Because conductors or metals are uniformly doped. Right. Next point. In semiconductor also, diffusion current can flows. Case 1. If semiconductor is non-uniformly doped. And if charge carriers are injected into a semiconductor, from one side, yeah. In these two cases, diffusion current can flows. Right. Write in a question. In classroom workbook, question number 8. In classroom workbook, question number 8. Write in a question. The electron concentration in n-type silicon sample. Varies linearly from 10 power 17 at x equal to 0. To TO2 6 into 10 power 16, 6 into 10 power 16 at x equal to 2 micrometer. At x equal to 2 micrometer. If diffusion constant of electron is, if diffusion constant of electron is 35 centimeter square per second, 35 centimeter square per second, then current density in the sample will be, current density in the sample will be, right. Now read the question once, all of you. What is the given data? What is the given data? The given concentration is, electron concentration is varies from linearly from 10 power 17 at x equal to 0. See here I am considering concentration versus plot actually. Versus distance plot x. Here the concentration is n and the distance is x. At x equal to 0, how much concentration here? 10 power 17. It is linearly varies, right? And at x equal to 2 micrometer, 2 micrometer, what is the concentration actually? The concentration is 6 into 10 power 16, right? Also they given a diffusion constant of an electron, how much? 35 centimeter square per second. Yeah, what we want to calculate actually current density in the sample, right? Here clearly I think the concentration is varies from high concentration to low concentration, right? So which current will flow? Diffusion current. That means which diffusion? JN diffusion, because it is an n-type sample, right? JN diffusion due to electrons is nothing but E into dN by dx. So what is the charge of electron? 1.6 into 10 power minus 19, dN value 35. Change in concentration, how much? This is 10 power 17 minus 6 into 10 power 16. Change in the distance, that is 0 minus 2 into 10 power minus 4. Actually here all majority parameters are in centimeters but except the distance, right? So here convert this one also be into centimeters, that is 2 into 10 power minus 4. Now what is the answer? That is minus 1120 ampere per centimeter square, right? You know this negative sign indicates here the diffusion current can flow in negative x direction actually. Negative x direction, right? Copy. Right. And next topic, relation between, next topic, relation between mobility and diffusion constant. Relation between mobility and diffusion constant, right? So now, see the relation between mobility and diffusion constant is given by Einstein relation, right? See what is the Einstein relation actually? Einstein relation is nothing but dn by mu n is equal to dp by mu p, which is equal to vt. Right, this is the Einstein relation actually. Okay, here what is vt here? This vt is nothing but thermal voltage. Thermal voltage, right? Here what is the vt here? Vt is nothing but kt by q. Kt by q, right? At room temperature means 300 degrees Kelvin. What is the vt value here? Vt is nothing but 26 millivolts. Right? Now I can also define the units of mu n by dn or q by k bar into t. Actually, what is the value of dn by mu n actually? Vt, right? Now here I want to calculate units of mu n by dn. Nothing but what actually? Simply it is a volt inverse. See, dn by mu n is nothing but volt. So mu n by dn is nothing but volt inverse. Right? Right down. Relation between mobility and diffusion constant is given by Einstein relation. Relation. Right. That is copy. Yeah. Next, write in a question in classroom workbook, question number 9. In classroom workbook, question number 9. Yeah. Free electron in a semiconductor sample. Free electron in a semiconductor sample have mean free lifetime of 5 into 10 power minus 14 second. 5 into 10 power minus 14 second at a room temperature. If Mn equal to 0.5 m naught, then calculate mobility and diffusion constant of electron A's. Diffusion constant of electron A's. Right. Now, I'll read the question once. Actually, what is the given data? They given a carrier lifetime, right, of free electron. How much? That is 5 into 10 power minus 14. Actually, carrier lifetime is indicated with this tau n, right? Seconds. And also they given Mn equal to 0.5 m naught. What is Mn here? You know, Mn is nothing but effective mass of an electron, and m naught is nothing but actual mass. I think you know what is the value of actual mass? 9.1 into 10 to the power of minus 31, right? Now what we want to calculate here? Mobility and diffusion constant, right? Here, what is the relation between mobility and carrier lifetime and mass actually? We know mu equal to E tau by Mn, right? Now from this actually mu n equal to E is nothing but charge of electron, that is 1.6 into 10 power minus 19, carrier lifetime, that is 5 into 10 power minus 14, Mn is nothing but 0.5 into 9.1 into 10 to the power of minus 31. So this is equal to how much? 0.017 meter square per volt second. This is the mobility value here. And one more we want to calculate, that is what actually diffusion constant of free electron. Here what is the relation between diffusion constant and mobility actually? That is Einstein relation, that is dN by mu n equal to Vt, right? From this dN equal to Vt into mu n. What is the value of Vt here? Vt is nothing but 26 millivolts into mu n, that is 0.017. So which is equal to 4.57 into 10 to the power of minus 4 meter square per second. This is mobility and diffusion constant, right? Copy. Yeah. Next topic, Hall effect. Next topic, Hall effect. Right. See, what is Hall effect actually? See, Hall effect means consider a specimen. Consider a specimen. The specimen is a metal or a semiconductor which is carrying a current. And is placed in a magnetic field. Then the Lorentz force is induced. Due to this Lorentz force actually, the charge carriers are bending towards Lorentz force. The charge carriers are bending towards the direction of Lorentz force, okay, due to which electric field is induced, which is perpendicular to both current as well as magnetic field. This process of inducing of an electric field is called as Hall effect, right? So this is the statement of Hall effect actually, right? First write down the statement. Consider a specimen. Write in a statement, consider a specimen in bracket metal or semiconductor. Metal or semiconductor which is carrying a current, and is placed in a perpendicular magnetic field, due to which Lorentz force is induced. Right. Next. Due to this Lorentz force, charge carriers are moving towards direction of the Lorentz force, due to which electric field is induced, which is perpendicular to both current and magnetic field. This process of producing of electric field is called as Hall effect. Right. This is the statement of Hall effect actually. Now I am going to prove this Hall effect actually. Next heading, proof. Copy this figure. Right. See here, to prove the Hall effect, actually here I am considering a specimen is a metal. Considering a specimen is a metal. Metal means charge carriers are electrons, right? See, consider a metal which is carrying a current, I in positive x direction, which is carrying a current I in positive x direction, and is placed in a perpendicular magnetic field in positive z direction. Then the Lorentz force is induced in negative y direction. Here, the Lorentz force is induced in negative y direction. This is the negative y direction, right? So, and it is given by Fy equal to Q cross V cross B, right? Here, this velocity is in x direction, magnetic field in z direction, right? You know, see, when the charge is negative in this, so when the charge is negative, this Lorentz force is acting oppositely to the V cross B. Means the direction of the Lorentz force and the direction of the V cross B both will be opposite when charge is negative. Similarly, when the charge is positive, then the direction of the Lorentz force and the direction of the V cross B in the same direction. Right? Write down this point up to this. Write down. Consider a metal which is carrying a current in positive x direction, and it is placed in a perpendicular magnetic field in positive z direction, due to which Lorentz force is induced in negative y direction, and it is given by write down Fy equal to Q cross V cross B. Right. This is the Lorentz force offered by the metal. Right. Next point. When Q is negative. Then the Lorentz force is acting. Oppositely to the V cross B. The Lorentz force is acting oppositely to the V cross B. Right. Next, when Q is positive, the Lorentz force is acting along the V cross B. Along the V cross B. Right. Next, soon all of you. See, due to this Lorentz force, what happened actually? The electrons are bending towards downwards. Why? I already told you, due to this Lorentz force actually, the charge carriers are bent toward the direction of the Lorentz force. Here, what is the direction of the Lorentz force? Towards negative y direction, right? Here, electrons also bend towards negative y direction, right? So due to which what happened, this slab 1 become negative. Slab 1 is negative. Slab 1 is negative means relatively the slab 2 is positive. Okay, slab 2 is positive means electric field is induced between the slab 1 and slab 2, which is perpendicular to both the current and magnetic field, right? This process of inducing of electric field is called as Hall effect, right? Right down, right down. Due to this Lorentz force, due to this Lorentz force, electrons are bending towards downwards. Electrons are bending towards downwards, due to which slab 1 become negative, due to which slab 1 become negative. Relatively, slab 2 become positive. Relatively, slab 2 become positive. Hence, next point, hence, electric field is induced between slab 1 and slab 2. Between slab 1 and slab 2. Slab 1 and slab 2. Yeah. How to calculate that induced electric field between slab 1 and slab 2? See, all of you. See, at equilibrium position, at equilibrium condition, this electrical force will balance this magnetical force to balance this Lorentz force actually, right? At equilibrium position actually, this electrical force is equal to magnetical force because a current carrying conductor is placed in a magnetic field, right? Then Lorentz force is induced. To balance this Lorentz force actually, the electrical force is equal to magnetical force. What is an electrical force actually? That is minus E into capital E, right? And what is the magnetical force actually? B into E into Vx, right? Now E cancel. Now this is the induced electric field within a specimen. But actually, what is the statement actually? A current carrying conductor is placed in a magnetic field. But here our equation is in terms of magnetic field and velocity. Convert this in terms of current actually, right? How to convert? See, we know what is the relation between current density and velocity actually? We know J equal to N into E into V, right? So from this, what about the Vx actually? The Vx is nothing but Jx by N. This is equation 2, right? Now from equation 1 and equation 2, right? Now Ey equal to minus Bz into Jx by Ne, right? Now here, what is the current density in terms of current actually? I by A. Bz into Ix by A into Ne, right? So this is the induced electric field within a specimen, right? Now I can also convert this in terms of potential actually, right? What is electric field in terms of potential actually? That is voltage per unit distance, that is V by D, equal to minus Bz into Ix by, what is the area from this figure actually? Okay, wideness into thickness. This is the thickness and this is the wideness actually. So this is W into D into Ne. Here DD cancel. Then what is the Vy actually? Here Vy is nothing but minus Bz into Ix by W into Ne, right? This is the induced voltage between the slab and slab 2. So this voltage is called as what actually? Hall voltage. Hall voltage, right? Copy. At equilibrium condition, copy the derivation. Topic Hall coefficient. Hall coefficient, it is denoted with RH. See, what is Hall coefficient? You know, Hall coefficient is nothing but reciprocal of charge density is called as Hall coefficient. That is RH equal to 1 by rho v, which is equal to 1 by Ne. Right? Rho v is nothing but Ne, where N is nothing but carrier concentration, free electron concentration. Right? E is nothing but charge of an electron. Now I can also define the units of Hall coefficient. Right? Tell me what are the units of charge, coulombs, and what are the units of concentration per centimeter cube or per meter cube. That means simply it is centimeter cube per coulomb or meter cube per coulomb. Right. This is the units of RH. Now I can also derive a relation between Hall coefficient and Hall voltage. Right. See here, what is Hall voltage? Actually, Hall voltage Vy is nothing but minus Bz into Ix by W into Ne. Tell me what is the 1 by Ne value? Actually, 1 by Ne is nothing but RH. Now Vy equal to minus Bz into Ix into RH by W. So this is the relation between Hall voltage and Hall coefficient. Very, very important relation. Copy. Add in the notes. Hall coefficient. It is the reciprocal of charge density. It is the reciprocal of charge density. That is RH equal to 1, which is equal to 1 by Ne, which is equal to 1 by Ne. Right? Copy units of RH and copy the relation. Right. Next, applications. Applications of Hall effect. Next one, applications of Hall effect. Right. See, the first application of Hall effect actually, you know, this Hall effect is used actually to determine whether the semiconductor is N-type or P-type. To determine whether the semiconductor is N-type or P-type. See, for N-type semiconductor. See, for N-type semiconductor actually, if it is an N-type, you know the slab 1 is negative. Slab 1 is negative and the slab 2 is positive. Slab 2 is positive. Okay, if it is a P-type semiconductor, actually, then the slab 1 is positive and the slab 2 is negative. Right on the first application, it is used to determine whether the semiconductor is N-type, or P-type. Right. Copy this one. For N-type semiconductor, slab 1 is negative. Slab 1 is negative. Slab 2 is positive. Next, for P-type semiconductor, the slab 1 is positive. Slab 1 is positive and slab 2 is negative. Slab 2 is negative. Slab 2 is negative. Slab based negative, right. Next. And one more application. You know, this Hall effect is used actually to find out the carrier concentration in a material, right? Yeah, how to calculate with help of Hall effect carrier concentration, right? See all of you. We know Hall coefficient is what? Hall coefficient is equal to 1 by Ne, right? You know, for metal, right? Hall coefficient is nothing but minus 1 by Ne. From this actually, what about N actually? N is nothing but minus 1 by RH into E, right? Now with help of this equation, we can calculate the carrier concentration in a metal. Similarly for N-type semiconductor. Okay, for N-type semiconductor actually, what will be the Hall coefficient value? Hall coefficient is nothing but minus 1 by N into E. But what is N actually here? N is nothing but Nd into E. So from this equation, we can calculate the donor concentration actually in case of N-type. Similarly for P-type. So for P-type semiconductor actually, what will be the Hall coefficient RH actually? RH is nothing but, okay, 1 by PE, where P is nothing but 1 by Na into E, right? Alright. With help of this expression, we can calculate the acceptor concentration. So in this way, we can calculate the carrier concentration by using Hall effect, right? Write down. Second application, write down. It is used to calculate carrier concentration. Right? Copy. Right. And one more application actually. You know, this Hall effect is used to calculate the mobility of the charge carrier, right? How to calculate the mobility of a charge carrier? So we know conductivity, right? What is the conductivity actually? N into E into mu. What is Ne in terms of Hall coefficient actually? 1 by RH, right? So from this mu equal to what actually? Mu is nothing but sigma into RH. So with help of this expression actually we can calculate what mobility of the charge carrier with help of Hall effect. Right on? It is used to calculate mobility of the charge carrier. Right? Copy. Right. And one more application actually. See, this Hall effect is used. Actually, this Hall effect is used as a Hall transducer. Yeah. How it can be used as a transducer actually? What is a transducer? Transducer is nothing but convert one form of energy to another form of energy, right? How it can be convert one form of energy to another form of energy? Please remember the statement. What is the statement actually? See, consider current carrying specimen which is placed in a magnetic field, then it can produce what? Electric field. If you are placing in a magnetic field, then it can produce what actually? Electric field. That means it will convert one form of energy to another form of energy. Simply we can say it can be used as a Hall transducer. Right on? It can be used as a Hall transducer. Right. And one more application of Hall effect, right? You know, this Hall effect can be used as a Hall multiplier actually. Yeah, it can also be used as a multiplier. Yeah. How it can be used as a multiplier? What is the relation between Hall voltage and current actually? Vy equal to minus Vz into Ix by W into Na, right? See, what is the statement of Hall effect actually? Consider a current carrying specimen placed in a magnetic field. That means what are the inputs of Hall effect actually? Current and magnetic field, right? Okay, then it induces what actually? Electric field, nothing but voltage, right? Now see here, our output is what actually? Hall voltage is proportional to multiplication of magnetic field, product of magnetic field as well as current. That means simply we can say it can be used as a Hall multiplier. right? Right up. It is used as a Hall multiplier. Hall multiplier. Right. Next, and one more application actually. This Hall effect is used actually to measure the power of EM wave signal. EM wave means electromagnetical wave, right? How to measure a power of EM wave signal actually? We know pointing vector. What is the pointing vector actually? E cross H, right? See, in Hall effect actually we know the electric field component and the magnetic field component. Then we can measure the pointing vector. That means we can measure a power of a EM wave signal, right? Right on. It is used. It is used to measure of power of a EM wave signal. Power of It is used to measure power of EM wave signal, right? EM wave signal. Yeah, this is about applications of Hall effect. Yeah. Thank you. To be continued in next lecture.